I'm going to discuss another example. We are given the temperature distribution in a plate, and we are not given directly the function, but we are given the idea that it's inversely proportional to the distance of the origin from the point A. Point A is xy. We find the distance and we say that is the proportionality. But given here the value of the temperature at a certain point. So that will help us to find the constant of proportionality and to define our function. The next steps are the same as we have given the function, and we can find the directional derivative, rate of change, increasing most rapidly, decreasing most rapidly. So that's the same as we are doing in the last example. Here the trick is that we have to formulate the function. So I'm having here the distance d from the origin is equal to root of x square plus y square. So given to me, my function txy is inversely proportional to the distance of this one from the origin. So this one here I change the constant proportionality and write an equation. This txy is equal to k times root of x square plus y square. We're given the information that our temperature at the point P to 34 is equal to 100 degree Fahrenheit. So T34 means x equal to 3 and y equal to 4. When you take x equal to 3, y equal to 4, is k over 9 plus 16 is equal to 100. When you solve this equation, you get here k over 25 into the root is equal to 5 is equal to 100, and this implies our k is equal to 100 into 5 is 500. And I can rewrite my temperature distribution function txy is equal to, put the value of k is 500 over under root sine of x squared plus y square. So this is my function. Now I go further, and my part A is the rate of change. Rate of change is directional derivative. If we want to find the rate of change of the function at the point 34 in direction of vector I plus j. So my rate of change is mean that I want to find the directional derivative of the function at the point 34 in direction of vector u, and that's here my gradient of the function here, gradient of the function t at the point 34 into the unit vector u. So I have to find the gradient, I have to find the unit vector, I substitute, I get my result into u. So I find first the gradient of the function t at point xy. So this is partial t by partial x I plus partial t by partial y j. So I take the derivative of this one. We are having here the under root sine function, and we can write the partial t by partial x, partial t by partial x will be equal to minus 500x over, we are having the value of x square plus y square to power 3 by 2. So we get 1 by 2, and then we having this 2x, 2 is considered 2, we get minus 500 I, and similarly to this one we get here minus 500 y over x square plus y square to power 3 by 2. Yeah, so this is my gradient. Now I find the gradient at the point x equal to 3, y equal to 4 at the point 3, 4. I recheck my point again, so this is very important. So we have point P is 3, 4, and here we put the value of x3 and 4. So I will get here minus 1500 over, when we having this is 9, so 9 plus 16, 25 to power 3 by 2 I plus, get here minus 500 multiplied by 4 is 2000 over 25 to power 3 by 2 j. I simply simplify this one, and I will get here the result of this is equal to here minus 100, 500 125 I minus 2000 over 125 j. Because we have the root sign, to get 5 to the power 3 is 125. Now I need here my vector A given to me is I plus j. So magnitude of vector A is equal to root of 2. I can get here unit vector is equal to 1 by 2 root I plus 1 by 2 root j. So when I want to find the direction, that's the directional derivative of the function at the point 34 is equal to gradient. My gradient is minus 1500 over 125 and I then minus 2000 or 125 j dot product plus 1 upon root 2 I plus 1 upon root 2 j is equal to minus 12 I minus 16 j dot product is 1 upon root 2 I plus 1 upon root 2 j. So when you multiply this one, we'll get here the result of this one is equal to minus 12 over root of 2, and then here is minus 16 over root of 2 is equal to minus 28 over root of 2, and that's the result I will get here for the rate of change of the function t at the point 34 in direction of the vector a, that's I plus j. This is the part A. Now I go to the part B. What's my part B? My part B is in what direction t increases most rapidly at B. The direction in which increases most rapidly is the direction of the gradient. So we have already gradient. We just take this direction as we simplify this one here is equal to minus 12i minus 16j. So this is my direction. So B, we have the t increases most rapidly. T increases most rapidly in direction of the gradient, in direction of gradient t at the point 34, and that's minus 12i minus 16j. Then part C of this problem is that we want to find here in what direction does t decrease most rapidly. Increase most rapidity is plus sign, and t decreases most rapidly. So we are having here the value of t decreasing most rapidly. T decreases, as we have mentioned before, rapidly will be minus gradient, rapidly in direction of minus gradient t 34, and we multiply with minus. The direction is to 12i plus 16j. So that's my part C. Let the direction be a vector B with the components b1 and b2. We want to find b1 and b2. The idea is that the directional derivative of the function at point 34 at direction of u must be equal to 0. And this is equal to 0 means the gradient of t at the point 34 into vector b is equal to 0. What's my gradient? My gradient is minus 12 minus 16, and 1 by b is equal to b1 and b2. And this must be 0. I get a dot product, we get 12 b1 minus 16 b2 is equal to 0. Now I can find here minus, I have here 12 b1 is equal to minus 16 b2. So either I take b1 or b2, we can find the other one. We say here let our b1, b2 is equal to minus 3, for example. So we get here 12 b1 is equal to 48. This implies b1 is equal to 4, and our b is equal to 4 and minus 3. So here we have let. So if we can say b is any real number, let b is equal to, we having here b1, we can rewrite this one by b1 is equal to minus 16 by 4 is minus 4 by 3 b2. So we can have here, when we take let b is equal to 3, and we having b1 equal to minus 4, b is equal to minus 3, b1 is equal to 4, and so on. We can take here b can be any real number. B can be any real number, and we can find here let b equal b1 equal to let b2 equal to t. When we take b2 equal to t, then we say here b1 is equal to minus 4 over 3 t. So we can have the vector b, general vector b is equal to, we are having here b is equal to minus 4 by 3 t, and t, where t is any real number. So is the direction, is the direction, b is the direction, where this is the direction, this is the direction in which the gradient of the function, the 0.34 direction of this is 0. So that's the idea. We can find the direction in which this is equal to 0. This we can just have a particular case by taking t equal to -3, or we can have a general case and take b2 equal to t, and then we find the value of b1. So this is the idea we're having in this problem. There are many problems in all the books of the calculus regarding this chapter, especially on the gradient and directional derivative. There are a lot of applications, so you have to do it. There are other problems in my notes. I'm going to put my notes in the description for PDF file. You can take the PDF file from there, and you can do the practice from there also. So main thing, as I always say, you can learn mathematics by doing practice. As much as practice you do, so you master your math, and the things become very easy for you. If you are students of engineering or you are students of physics, these mathematics, well, these things are like a tool. So when you learn it nicely, then you can apply them in your own subjects, and you can have more easy life, and you understand things more correctly. So don't underestimate this math work, especially these are the techniques, these are the tools you need to master your own subject. Thank you very much.